the phone from the previous video, I'm going to explain hydrogen gets always delta plus partial charge. And examples are HF, water, methanol, ammonia, methylamine, so, and any amine, right? So I'm showing here, so electronegative atoms, fluorine, oxygen, nitrogen gets delta negative, and it's going to attract to the neighboring molecules with IMF attractions, intermolecular forces. So these are the dashed green lines are the ones actually attractions in between molecules, right? So this type also dipole-dipole due to permanent dipoles. That's how you get this phone and making hydrogen bonding. I call them VIP dipoles because you see here's a double helical DNA. This is called the alpha helix, and the other one is called the beta sheets in the secondary protein structures. And they all have hydrogen bonding. That's why it's important actually. Now, the second ranking category is dipole-dipole. Let's get an example, something like HCl. So Cl gets delta negative due to electronegativity, and then hydrogen is delta plus. There is the attraction between two molecules, right? So these are called the permanent dipoles, right? So they are lesser than the hydrogen bonding dipole-dipole in their ranking. Right? Now there are two simple categories here. One is called the ion dipole and the other one is called induced dipole. So the ion dipole, induced dipole, yes. And ion dipole is actually about when you add something like sodium chloride, a salt electrolyte into the water, how the ions gonna dissolve. It's really important to know. So the sodium chloride breaks sodium plus and chloride minus, and it's surrounded by water, especially projecting the oxygen delta negative towards sodium plus. It makes a nice cage. It's called the solvent cage. And then the chloride negative actually nicely nestled by, snuggled by the H hydrogens of the water molecules. And they are delta plus and the chloride is negative ion, so they attract nicely. That's a solvent cage. That's how the salts can be dissolved, right? The induced one is different. So if I have, let's say, H2S, S gets delta minus, H gets delta plus, those are permanent dipoles. If I bring in a closer hydrogen molecule, H2, which is non-polar, it's going to charge the hydrogen molecule into a different shape, giving it a induced dipole, delta minus, delta plus. The electron cloud pushed into a pear shape and it will make induced dipole. So that's a dipole-dipole second category. The third category is the weakest one out of the intermolecular forces. This is called the London dispersions, sometimes forces, sometimes we call LDF or sometimes LD. And sometimes it's called the Van der Waals forces, okay? And all these names are true, but then what's this one is, especially the time, is very short time, transient. Very little amount of time they exist. They exist in non-polar molecules like hydrogen, nitrogen, oxygen gases, of course, all the inert gases, they all are non-polar. They don't dissolve in the water. But how come they become liquids? This is how it does, right? This is what happens. So if you bring helium, they are symmetric, they are non-polar, but their electron cloud is moving so fast, it's going to make into an elliptical shape. And the one end is less denser, the other end is more dense in electrons. So that makes transient delta plus and delta minus. Now you have a little bit of an induced dipole, right? And for the very little time. So that's how you get the London dispersion, right? So because of the London dispersion, we get this long chain carbon chains, right? Even short carbon chains, hydrocarbons. They are going to be nicely packed into a liquid, longer ones, because of this London dispersion, right? This is a packing effect I'm showing. And also if you have like this kind of branched ones, they also make liquids, but they're lesser.